All right, now we're moving on to rational functions. So the objectives of this lesson are for you to be able to sketch a graph of the rational function, and then for you to be able to solve and evaluate using rational expressions. Okay, so in example one, you'll see we'll be graphing the basic rational functions. Example two, you'll be graphing the complex ones. Those ones involve multiple vertical asymptotes or a diagonal asymptote. And then for example three, that's when you will be solving and evaluating using the rational expressions. All right, so example one, we're going to start with the basic graphs first. So here you can see our function is -1 over x minus 2 plus 4. This is actually a transformation of your parent function, 1 over x. So in this case, you could use your transformation properties to help you graph it. But as we get to more complex ones, you'll see that that's not as effective. So instead of using the transformations on this, we're actually going to go to a different template. But I just want to let you know that in this format, you could actually apply transformations and do the graph as well. Okay, so what makes this a rational function, in case you didn't know, is this part right here, the -1 over x minus 2. The reason why that is a rational function is because you got a fraction, and inside the fraction, you've got a function in there. Okay, so something like x, x squared, x cubed, any sort of polynomial expression, as long as you have a fraction that contains that, you will be dealing with a rational function. All right? Okay, so how do you graph the rational functions? You can still kind of follow the same template that we use for the polynomials, step 1, step 2, step 3. So if you remember, step 1 was all about the end behavior, step 2 was all about the intercepts, and then step 3 was kind of to use an interval table. Okay, so we're still kind of going to do the same thing. It's just going to be used a little bit differently. Okay, so for our end behavior, what you'll see here is that your graphs are actually going to have end behaviors going up and down and left and right. So because of that, you are going to have to evaluate the horizontal asymptote, and you're going to have to evaluate the vertical asymptote. Okay. The horizontal is always going to happen, at least for this format of the problem. Whenever your problem looks like this, the horizontal is going to always be this value over here. So this will always be your HA. And then your vertical asymptote is always going to be the denominator of your fractional part. Okay. So for your horizontal, it's pretty straightforward. All you have is the 4 there. You just have to know how to write it. Remember, if you're trying to write an expression for any horizontal line, that always goes y equals something. So in this case, we'll say y equals 4 because we have a 4 right here. All right. For the vertical, I told you you're supposed to look at the denominator. So really, if you recall, the only way you're going to get a vertical dotted line whenever you're dealing with denominators and stuff is whenever the denominator is equal to 0, that's when you have a vertical dotted line. So no different here. What you have to do then is take your denominator, set it equal to 0, solve for x. In this case, pretty simple. That's going to be at 2. Okay, so your two dotted lines that are going to basically help dictate your end behavior or help you sketch the graph in this case are going to be at y equals 4 and x equals 2. So if you want to graph that real fast, just so you know what it looks like on the graph, at x equals 2, that'll be somewhere here. Okay, so you literally just draw a dotted line going up and down. I would prefer you put a little number at the end of the dotted line just so I know where you're graphing it, because sometimes depending on how messy or how neat you are, it's not that easy to tell. And then for our horizontal dotted line, that's the y equals 4. That'll be 1, 2, 3, 4. You're going to draw a horizontal one going this way at 4. Okay? So if you notice now, these dotted lines, what you've done is you've kind of split your graph into 4 regions. And what you'll see is that your final graph will show up in 2 of those 4 regions. You just got to figure out where. Okay? So that's where you need to start finding some points so you can start connecting the dots. So step 2 will help you find some of those points. That one, let's see. That one, we're talking about your intercepts. So again, intercepts, you're always talking about either your x or your y-intercept. Okay. Your y-intercept, again, that is when x is equal to 0. You plug it in and you get your answer, right? So if you look back over here, if I erase some of this stuff just so you can see what your original function was. Okay. You've got, if you plug in a 0 into here, you basically got -1 over -2 plus 4. And if you do the math over here, that looks like it's 1/2 plus 4, so it's going to be 4.5. Okay, so that means at 4.5, again, this was at 4, so just a little bit above it, you've got a dot. Okay, so you might think not so helpful, but actually it is pretty helpful because what it's telling you then is that for sure somewhere in this region you're going to have some graph. Okay, so you've already found one of them. Now you got to figure out the other region to help you out. So in this case, your y-intercept's right here, and then maybe finding your x-intercept will help you too. Now, remember for your x-intercept, that's when you plug in a 0 for your y, and then you figure out what your x is. Okay, so when you do that, kind of running out of room here. Let me just go down here. That means I'm going to set -1 over x minus 2 plus 4 equal to 0. So what I can do is move the 4 to the other side. That'll make it -1. X minus 2 is equal to -4. I can cross multiply. That'll make it -1 equals -4x, I think, plus 8. And then if I move it to the other side, it looks like I'm going to get -9 and then divided by -4 equals x. So it looks like x is going to equal to, what is 9 over 4? It's like 2 1/4. Okay, so it looks like x is going to equal to 2.25. So according to this, somewhere at 2.25, so like somewhere around here, I'm going to have some graph as well. Okay, so really, in this case, that's all that step 2 gave you. If you recall before with the polynomials, step 2 gave you pretty much all the critical information. Here it gives you some helpful information, but as you can see, just having these 2 dots doesn't make it as obvious, what your graph's going to look like. If anything, I would say for the rational functions, step 1 is a little more important because without these dotted lines, you really have no idea how you're supposed to sketch your graph. Okay, but the last part here, the interval table, that should help kind of like put everything together. So for the interval table, what I want you to do is I want you to take your vertical asymptote. So in this case, we only have one. And the idea is I want you to pick some points going to the left of it and pick some points going to the right of it. And hopefully that'll help you get enough extra points to get a better sketch of what's going on. So our vertical is at 2, right? So to the left, you might want to pick some points like 1. You don't have to pick 0 anymore because you found it, and maybe pick one more point then. So let's pick like -1, okay? So what you'll see over here is I'll put the L to show you that this table is to represent the left side of the horizontal or of the vertical asymptote. We already discussed the 2 points we might want to pick here is 1 and -1. So what you'll do then is take these guys, plug them in here, and then get y values. Okay, so when I do that, this is what I'm going to get for my y values. All right, so when I plugged them in, I found that at 1, I got 5. And then at -1, I got 4.33. Okay, so when I go back to the graph over here, let's see. This one was at 4.5, right? So that means at 1, I'm just a little bit above, somewhere around here. And then at -1, that's somewhere over here, I'm at 4.33. So again, just a little bit below the y-intercept point over there. Okay. On the right-hand side, if you want to figure out points over there, again, our vertical is right here at 2. So to the right, you probably want to choose numbers like 3, 4, 5, something like that. Okay, so for the right hand side, I'm going to pick 3 and 4. Okay, when I pick 3, I'm going to get 3, and when I pick 4, I'm going to get 3.5. Again, what I'm doing here is I am taking these x values, I'm plugging them directly into here, and then evaluating what my y values are. Okay, so if I graph that real fast on here, again, this one I probably put a little too much to the right. So let's just fix that. Let's make that closer to 2 since it's 2.25. So let's put that more somewhere over here. At 3 then, I'm going to be at 3. So 1, 2, 3. And then at 4, I'm going to be at 3.5. So at 4, I'm going to be like somewhere around here. Okay. So the idea is this. I'll graph it with a different color so you can see it. Right now, for sure, you know this is how your dots connect, right? But then afterwards, you run out of dots unless you're willing to put more dots in the table. But you really don't have to, because this is where these dotted lines come into play. Again, these dotted lines are to help you control the end behavior. In other words, as your graph continues extending, it should run along those dotted lines. So in this case, what you'll see then is what makes the most sense is that this red, or this graph over here that I'm graphing in red, it should continue along here through the dotted line, and then over here it should shoot up like that. And then same idea over here. If you connect the dots on this side, you've got these three, but then afterwards, to finish it, you should make it run along those dotted lines. Okay, so this is your graph for this function over here. Okay, so again, as I told you before, we can still use step 1, step 2, step 3. This time I won't make you label it because it gets kind of messy when you try to label it S1, S2, S3 on this stuff, but just kind of know what you're doing here. So again, S1 is still your end behavior. In this case, you had 4 of them. You had this, 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 and this. And again, to find those end behaviors, it was critical that you figured out the horizontal and vertical asymptote. Okay, so that's what we did here. And then for step 2, again, we found the intercepts. But again, the intercepts this time, let's put them in green. They didn't give you that much information. So you got that dot over here and you got that dot over here. It's a little bit helpful, definitely, but in terms of helping you really get an idea what the graph is going to look like, really what was more important was step 3 in this case, where you found a couple more points. That's this and this, that and that. And then that kind of helped you sketch in everything along with the end behavior. Okay, so this is kind of the approach that I would like you to use when you're sketching those rational functions. Okay, so step 1, end behavior, always critical. Make sure you do that. Step 2, to be honest with you, if you want to skip step 2 in here, not such a big deal with me, because step 3, when you graph the additional points on there, that should help you figure out everything else. Okay. All right, so let's look at the next example then. Okay, so for this one, we've got f of x is equal to 2x minus 5, and then over x plus 3. Again, as I mentioned before, whenever you have a function inside the fraction, either on the top or the bottom or both, that's what makes this a rational function. Okay, so for this one, again, we're still going to use the same steps as before. Okay, so I'm still going to want to use step 1, step 2, step 3. Again, step 3, not as critical anymore, so in this case, I'm just going to kind of skip it. But step 1, you definitely want to figure out the end behavior still, and then step 3, you definitely want to figure out your tables to help you get some extra points. Okay. All right, so for the end behavior, again, we said we want to figure out our horizontal dotted line and we want to figure out our vertical dotted line. You'll notice for this rational function, this is not formatted the same way the other one was. Okay, the other one, you had basically a number on top, you had x minus or plus something on the bottom, and then you had another number at the end. So when it's in that exact format, we can take the number at the end and then the bottom to kind of help us figure out the information we want. When it's not in that exact format, which this one isn't, then you have to do something a little bit different, okay? So the vertical part turns out will still be the same. So you still want to look at the bottom of the fraction. So in other words, we want to look at x plus 3, set it equal to 0, and then that'll give us x equals -3. So that is still going to be the same as the previous one that we looked at, okay? But now for the horizontal, again, you're missing that number over here. And to be honest with you, even if you had the number over here, because this top part isn't just a 1 or a 2, like just a whole number over here, just using this number at the end turns out would not give you the correct horizontal asymptote. Okay, so when your rational function is purely a fraction like this, in other words, it doesn't have some extra part over here, how you're going to figure out your horizontal asymptote is you're going to have to look at it using a case-by-case scenario. Okay, so what I mean by that is for your horizontals, you've got 3 cases. Okay, you've got the case of a greater than b, you've got the case of a equal to b, and you've got the case of a less than b. And when I'm talking about a and b, what a and b are referring to are a and b are talking about the powers of the numerator and the denominator, okay? So if you look here, I've got my numerator up here. If I focus on just the x part, that's right here, right? Okay, so I only have one x here. There's really not much to focus on. It's just this one. What is the power that is associated with this? Well, that's going to be a 1. Okay, so in this case, that means my a is equal to 1. When I look at the bottom of my fraction, again, the only x I have is this one, so there's really not much debate here. You just got to look here, and then you got to figure out what is the power associated with this x over here. That, again, is also going to be 1. Okay, so that means my b is going to be 1. So in this case, when I look at a and b, they're equal, which means you are going to go with this condition over here. All right, so you can already imagine if, for example, in another situation, I found out that a was 2 and b was equal to 1, then if you go to our conditions, you would use this condition up top over here. Okay, but for our situation right now, our a is equal to 1, so that means we're going to deal with the middle condition. All right, so once you figure it out what your scenario is, then you go with what condition goes with it. So just so you know, whenever a is less than b, automatically you're going to have a dotted line at y equals 0. Whenever a is equal to b, you are actually going to say y is equal to the ratio of the coefficient, okay? And I'll show you that when we get there. And then lastly, when you have a greater than b, it turns out that your ha is going to turn into a saw. Okay, so what a saw is, it's a slanted asymptote. Okay, and to figure out the slanted asymptote, you're going to have to do some algebra with it, but we'll save that for later. I think that's in the complex section. Okay, so once again, whenever your, I'm just going to erase this right now. Whenever your function is given to you as purely a fraction, and it's got x's on the top and x's on the bottom, in order to figure out the horizontal portion, you want to go with this case-by-case scenario. Okay, so you always evaluate the biggest power of x on top, the biggest power of x on the bottom. So the top one you're going to call a, the bottom one you're going to call b. So depending on your scenario here, if a is greater than b, then you know you're going to have a slanted asymptote. If a is equal to b, which in our case that's what's going on here, you are going to find the horizontal asymptote by calculating the ratio of their coefficient. And then finally, if you have a scenario where a is less than b, then automatically it's going to be at y equals 0. Okay? All right, so going back up here then, so like we said, for this particular case, we've got a is equal to b, which means we're going to use the ratio of the coefficient as our horizontal asymptote. Okay, so what that means then is when you look at the x's, what are the numbers in front of the x? So in this case, I've got the 2 up top here. And then on the bottom, I don't see anything, but that means I've got an invisible 1 on the bottom. All right, so 2 over 1 is the same as 2, which means we are going to have a horizontal dotted line at y equals 2. Okay, so at this point, just like before, I would take this information and I would quickly sketch it on here, just so I have a visual as to what the graph is going to start looking like. So at y equals 2, that's over here. At x equals -3, that's going to be somewhere here. Okay. All right. So all I have to do now, if I skip step 2, is come up with enough dots for me to figure out where are my portions of the graph going to be. Are they going to be here and here? Are they going to be there and there? Are they both going to be on top? That's what the table is going to help you figure out, because it's going to help you determine where the dots are located. Okay. All right, so once again, when we go to the table, the first thing you do is you look at where your vertical is located, so that's at -3, and we're going to go now to the left of -3 and then to the right to kind of help us figure out where those dots should be located. So I'll make this one to the left of -3, I'll make this one to the right. So to the left of -3, we're talking about what? -4 and -5, and then to the right of -3, let's go with -2 and -1. Oops, sorry, put that in the wrong spot there. Okay, so now what I'm going to do is I'm going to take these guys and I'm going to plug them into the function and figure out what my y values are going to be. Okay, so when I do that, this is what I get. Okay, so it looks like when I plug in -4, I'm going to get 13. When I plug in -5, I'm going to get 7.5. When I plug in -2, I will get -9, and then -1 will get me -3.5. Okay, so let's graph it and see what's going on. So I'm at -4. That's over here. I'm at 13, which is somewhere up here. At -5, I'm at 7.5, which what was this at 2? So I don't know. Maybe it's like somewhere over here. Okay. On the right hand side at -2, I'm at -9, so that's like way down here somewhere. And then at -1, I'm at -3.5, which let's say it's somewhere over here. Okay, so you can graph a few more points if you want this graph to be a little more accurate. Again, I only need you to get a couple points here just so you know which region your graph is going to be located. So again, when we actually graph it, I know for sure these two dots are going to connect. And then how I'm going to finish it then is I'm just going to go along the end behavior. So this one, I would probably go something like this, and then have it go upwards like that. And then over here, I'll connect this for sure. And then if I wanted to go along the end behavior, I'll have it go here, and then I'll have it go down there. Okay, so that's basically a nice rough sketch of what 2x minus 5 over x plus 3 should look like. Again, you can make this look a little bit better by choosing a few extra points here, so you'd have a few more points here to help you make this a little more accurate, but at least you have enough points here to know which region the graph should be. All right. So if you've already kind of noticed, when we graph these, if you had one graph here, you don't normally see another one show up to the right. For sure, you can't have it show up down here, or else it won't pass the vertical line test. So something for you guys to keep in mind. I know a lot of times you'll just kind of put dots on there, and wherever they are, you'll graph them and you won't care. But some things make sense and some things don't make sense, right? So already I can tell you, when you have these simple graphs over here, what you'll notice a lot of times is wherever one of the graphs is, the other one is diagonally across from it. Okay, typically they're not like straight across from it, and again, they're never up and down from each other, or else they wouldn't pass the vertical line test. If we look at our previous answer, once again, this graph was up here, that one was on the other side, and therefore they were diagonally across from each other. Now for these two examples that I showed you, unfortunately I didn't come up with one that one was up here and one was down here, but just to let you know that is possible. Okay, so You can have them directly diagonally across from each other this way. You could have them going that way. The only one that I don't anticipate would happen in this case is that they were across from each other or if they were up and down from each other. All right? Okay, so those are your two examples for the basics, and then now let's move on to the complex. All right, we're now on example 2, so now we're going to be dealing with the complex rational functions. So here you can see we're going to be graphing f of x is equal to x over x squared minus 4. Now I know this may not seem that complex because there's not a lot of letters and variables in here, but what's going to make it complex is this bottom part over here. So again, whenever you set the bottom equal to 0, that'll get you your vertical dotted lines. As you can see in this case, when you set this equal to 0, you're going to come up with 2 answers, not just 1. So that means you're going to have 2 vertical lines, and 2 vertical lines means it's going to divide your graph into more regions for you to figure out what's going on. All right? Okay, so to get a better idea of what that's going to look like then, again, we can do our steps, step 1, step 2, and step 3. Okay, so step 1 is our end behavior. Step 2 is our intercepts. This time around, that's optional. Now, when I say optional, I know most of you probably read that as, great, I don't have to do it, I won't do it, I'm going to skip on to the other one. But to be honest, I mean, it can't hurt you. For these graphs, these complex ones, unless you're cheating and already looking at what the graph looks like on Desmos, a lot of times having those extra intercept points might actually be able to help you determine what is going on in the middle of the graph. Okay, so again, it's optional. I won't make you do it, but to be honest with you, if you have the time, it wouldn't hurt. Sometimes it can be very helpful in helping you figure out what the graph is going to look like. Okay, so for our end behavior, we've got our horizontal, we've got our vertical. We've already discussed the vertical is going to be where the bottom is equal to 0, so that's x squared minus 4 equals 0. When you solve for it, you'll get x is equal to plus or minus 2. So I didn't show much work there. Hopefully you understand how I got that. I just moved the 4 to the other side and I square rooted both of them. Okay? All right, for your horizontals then, again, since this is in a complete fractional form, what you want to do is you want to figure out what's the a value up top, what's the b value on the bottom. Hopefully you can tell that a up top in this case is going to be 1. B on the bottom, that's the x squared, that's going to be 2. You have a case where 1 is less than 2, which means if you go back to the chart that we looked at, automatically you know that you have to have a horizontal here at y equals 0. Okay, so that means you've got dotted lines here and you've got dotted lines there. Okay, so you've got it at 2 and you've got it at -2. Okay, and you also have it at 0. Okay, so obviously the problem with drawing dotted lines on 0 is that you won't see them because the axis is covering them. So if ever your dotted line is on y equals 0, what I like to do is I just like to kind of extend it out here. Okay, and that way I know that at 0 I've got a dotted line as well. All right. Okay, so step 2, optional if you want to do it or not. I'm just going to skip to step 3 and see what's going on. So in this case, when you go to the table, understand that since you've got 2 vertical dotted lines now, you've got 3 regions in between to evaluate. Okay, so that means now when I go to step 3, I expect that you will have 3 tables that you're using to help you figure out what's going on. Okay, so you've got what's going on the left, what's going on in the middle, and what's going on the right. So to the left of -2, we're talking -3 and -4. In the middle, I've got 3 points there that I can evaluate, -1, 0, and 1. And then on the other part, on 2, to the right of 2, I've got 3 and 4 as well. Okay, so what I'm going to do now is I'm going to take all of these points, I'm going to plug them back into this function and see what I get for the y values. Okay. All right, so when I plugged it in, this is what I got. At -3, I got -0.6, so real small. At -4, I got -0.33, even smaller. At -1, I got 0.33. And then at 0, I got 0. And then this one I will leave as a mystery for now, and I'll explain why later. At 3, I've got 0.6, and at 4, I've got 0.33. Okay, so let's kind of graph this and see what happens at -3. I'm at -0.6, so basically somewhere over here, real close to the x-axis. At -4, I'm at -0.33, which again is hard to graph, but just basically make it a little bit higher than this point right here. So if I do that, that'll be right here. In the middle, at -1, I've got what? -1, I've got 0.33. And then at 0, I've got 0. Okay. And then on the right, at 3, I've got 0.6. So that's somewhere up here. And then at 4, just a little bit below it, somewhere over there. Okay. So if I try to graph it now, obviously I know that these two dots connect together. And then if I use my end behavior wisely, it would make sense that it would follow along this side and it would kind of curl down here. Okay. Now you might wonder, well, why wouldn't it, for example, why wouldn't it go here and then curl up to follow over here? And to be honest, it could. I would just guess in this case that it wouldn't because of this dotted line here. Now this is again where it might be beneficial for you to graph an additional point. If you decided to graph another point closer in between these two guys over here. So again, this one was at what, -2, and this one's at -3. So if you had graphed a -2.5 in this case, all right, let's see what I would have got if I got -2.5. At -2.5, you would have gotten -1.11, which is somewhere over here. And so now with that third dot, you would know for sure then that this would go from here and then follow downwards. Okay. So again, I'm not going to force you to because I know most of you guys are lazy and if you only have to graph two dots, you'll graph two dots. But as you can see, sometimes just having those two dots, it's hard to figure out, is it going to go here and then go up, or is it going to go here and then come down? Okay, so if you need to graph more points, like I said, it's not shameful to do that. A lot of times it's the difference between the correct graph and a slightly incorrect graph. Okay, so let's look at this next part over here. So in the middle, again, I've got these 2 points. So if I connect the dots on them, I've got this. For sure on the left-hand side, I would say if I'm going to continue following this, probably looks like it's going to go like this. But then on the right-hand side, I would say it's kind of tricky. You've got two options here. My graph, your graph could reasonably go this way and go along the dotted line here, or your graph could also hook back up and go up here. As you can see, having just two dots doesn't really tell you what's going to happen on this side. So again, I'm not going to force you to, but sometimes it is to your advantage, even though I only asked for two, for you to graph a couple more, just so you can see what is going on those sides. Because I know you guys aren't fortune tellers. There's no way you can tell right away what's going to happen. Okay, so if you had graphed that, or if you had evaluated that third point over here at 1, you would have seen that at 1, you get a value of negative 0.33. And that helps out a lot because that means your next dot is going to be over here. And if your next dot is over here, it's reasonable to assume that to finish off your graph, you're going to go like this. Okay. Same idea over here. So if I connect the graph, I know these two guys connect. I'll finish the end behavior up here. And I guess it's reasonable to assume that it would go straight across here. Okay, so if you look at it, this would be the graph of this over here. Okay, so what I want you to notice about this is that if I asked you, if you had to choose between even and odd, what kind of graph you would think this is, I think most of you would hopefully choose odd, okay, and that would be correct because Obviously in the middle, we've got that little snake function, and that always happens at x cubed. And then furthermore, you'll notice over here, I've got a graph that goes up here, and then I have a graph that is kind of like on the bottom of it. So if you remember, that's kind of like origin symmetry, okay? But bottom line, the reason why I'm pointing all this out to you, you'd obviously be able to figure this out if you graphed enough points, but as a way to kind of like quickly double check to see if your answer makes sense, if you look back at this function over here, some of you might look at this and say, this is going to dictate how my graph looks. It's actually this top part over here that dictates how the graph looks. So for this one, as you notice, x is an odd function, right? So it's because of this that you ended up with the snake here, and you ended up with the odd symmetry on this side, okay? This part over here, all this did was it just split these regions into two. So again, when you look at the function and you compare it to the graph, a lot of times that numerator is going to kind of dictate the shape or the symmetry of what your graph is going to look like. Okay, let's move on to the next example then. Okay, for our next example, we've got x squared over x squared minus x minus 2. So yeah, let's get to the steps and we can see what's going on. So step 1, we've got your end behavior. So again, you've got the horizontal and you've got the vertical. Okay, so for the vertical, you want to figure out when x squared minus x minus 2 is equal to 0. Do that however you want to. You can factor it, you can quad it. Basically, you should figure out that x is going to equal to 2 and negative 1. Okay. And then for your horizontal, again, we are going to look at the powers. So up top, you see x squared, which means a is equal to 2. On the bottom, you see x squared and you see x. The bigger one there is obviously x squared. So once again, 2 is the bigger power on the bottom. So when you compare these two then, obviously 2 and 2 are equal. When a is equal to b, that means we look at the ratio of the coefficients. So in front of the x squared over here is a 1. In front of the x squared over here is also a 1. 1 over 1 is the same as 1, which means we've got a horizontal at y equals 1. So now we graph everything. We've got our dotted line at 1. We've got our vertical at 2. And we've got it at negative 1. Okay. So once again, when we drew our dotted lines, it divided everything up into 3 vertical regions. So that means if you skip to step 3, you're once again going to have 3 tables to look at. Okay. So we're going to have one for the left side, one for the middle, and one for the right hand side. Okay. So if we look at what we've got here, at negative 1, if you want to go to the left, looks like we should be evaluating negative 2 and negative 3. If you look at the middle right here, between negative 1 and 2, the only nice whole numbers that I can see here would be 0 and 1. And then if you want to go to the right over here, looks like we're going to go with 3 and 4. Okay, so I will now take these values and I will plug them into here and then see what I get. Okay. Okay, so when I plug them in at negative 2, I got 1. Oops. 1. At negative 3, I got 0.9. At 0, I got 0. At 1, I got negative 0.5. At 3, I got 2.25. And at 4, I've got 1.6. Okay, so let's graph the points over here, see what's going on. So at negative 2, I am at 1, which ironically, is right on the dotted line here. Okay, so that might make you think, okay, I must have done something wrong, but just to let you know, this is possible. Okay, at -3, I am at 0.9, so at -3, I'm a little bit below here. Okay, and then at 0, I'm at 0, so that's here. At 1, I'm at -0.5, so that's somewhere here. And then at 3, I'm at 2.25, so at 3, I'm at somewhere up here. And at 4, I'm just a little bit below it, but still above 1, so somewhere over here. Okay, so if you look at it this time, to be honest, it's kind of tricky. Okay, if you connect the parts you know for sure, so if I connect this part, and I connect that part, and I connect that part, I would say only the part on the very right side for me makes sense. If I had to make a guess what would happen here, I would say it would continue going up here, and then it would go like that. Okay, here it's a little tricky because if you look at it, what do you think is going to happen? Because it already crossed the dotted line, right? So is it possibly going to go straight here, but then here, is it going to go up since it already crossed the line, or will it go back down? I mean, it's kind of hard to tell. So once again, this is one of those situations where if you're not sure, don't be lazy. Just graph another point to help you out. Like we're talking about here, it'd be really nice if I knew on this side whether or not I have another point up here or I had another point down here. It would help me figure out what to do next. Okay, here I don't need to figure out. You might be wondering, well, how come I don't need to figure out here? It's because I know that the dotted line is right here, so this one has to eventually go this way. Okay, now it may end up crossing up a little bit and passing this horizontal line again, but at the end of the day, I know it's got to go straight. It's not like, I think this one's going to go down here or it's going to go up here. I know it's got to go straight because that's where the dotted line is and it has to follow the end behavior. This one is tough because I don't know if it's going to go up or if it's going to go down. So in this case, I would suggest you graph an extra point to help out. So, or to help you figure it out. So for this one, we should graph an extra point at negative 1.5, I think. And then, so let's see what we get. So at negative 1.5, it looks like I get 1.3, okay? So 1.3 obviously is going to be somewhere up here, so that solves my mystery now. Now I know that my point should probably end up like that, okay? Now we get to the middle. Again, with the middle, unless it's obvious to you, it's not so obvious to me. I mean, I could go from here and go straight up, and then this one could go straight down. I could also guess that this one, I'm assuming this will go straight down here. I'm not 100% sure, but I assume this could go straight down here, and then from here, it could also maybe curve back down this way. So again, if you're not sure, don't be lazy, put a few more points in there. Okay, so I'm going to put an extra point in between here to see what's going to happen. I'm going to put an extra point in between here and see what will happen as well. And in order to do that, I'm going to have to pick some decimal numbers. So for the left-hand side, that means I want an extra point at, it looks like, negative 0.5. And then for the right-hand side, it looks like I want an extra point at 1.5. Okay, so when I plug that in at negative 0.5, I will get negative 0.2. And at 1.5, I believe I will get negative 1.8. Okay, so negative 0.2 I know is somewhere down here, and negative 1.8 obviously somewhere down here. So now, when I connect those dots together, okay, I think it's safe to assume that my graph is going to finish this way and that way. Okay, so this then would represent the graph of x squared over x squared minus x minus 2. Once again, if you think about it, now this is not perfect, but it kind of follows the pattern. Whenever you have two things like up, up, or down, down, that's even, right? And again, this one over here, this is a parabola. A parabola is represented by x squared, again, even. So if you look at the top over here, the top part, the numerator, was x squared, so the fact that the rest of this graph has even behavior over here and a parabola in the middle, that actually makes a lot of sense. Okay? Okay, let's look at our next example. We've got x squared plus 3x over x cubed plus 2x squared minus 9x minus 18. Okay, so as you can see here, it's going to be a little challenging to figure out the zeros on the bottom, but it's something that you should be more than capable of doing at this point. In fact, for this particular problem, instead of going to step 1 first, what I'm going to do is I'm going to go a little different this time, and I'm going to take the top and the bottom, and I'm going to break it down to its factors. Okay. So when I do that, let's start with the bottom over here. Turns out I can group factor this one, so that'll be x cubed plus 2x squared, and then minus 9x minus 18. So I can factor x squared out of the first one, giving me x plus 2. I can factor out negative 9 out of the second one, giving me x plus 2 again. That's good. The parentheses match. So now I can put it all together and call it x squared minus 9 and x plus 2. Okay. I can further break this down to x plus 3, x minus 3, and x plus 2. So this now becomes the complete factorization of this portion down here. So let me just rewrite that real fast so I remember. So I've got x plus 3, x minus 3, and x plus 2. Okay. On the top, when I factor this is pretty simple. This will just be x and then x plus 3. So what's important to see here once you've factored everything is that you'll notice on the top and on the bottom you have the exact same factor. That would be x plus 3. Whenever that happens, you should cancel that out and realize that at that location, x equals negative 3, you are going to end up with a hole. Okay, so we'll address that later. But perhaps what's more important than the hole itself is that knowing that you had to cancel these two items to create the hole over here, that means the x plus 3 on the bottom is not there anymore. Okay, and if it's not there anymore, then as you can see, instead of 3 dotted lines, you really only have 2. And to me, that's a major thing, because if you didn't realize to do this step over here, you would have graphed 3 vertical dotted lines when you got to your step 1, and that would have totally messed up your graph. There's no way to recover from that. Okay, so in this case, it was very important for this problem, before you actually went to the end behavior and then to your tables, to actually know to cancel out one of the factors, so that you know how many dotted lines you're actually going to draw here. Okay, now if you're wondering, well, how'd you even know to do that? You didn't do that on the other problems. That's because I knew on the other problems, if I factored them, nothing was going to cancel out. Okay, it's really just experience at this point. If you want to play it safe, I suggest you always start your problem by factoring and then seeing if something cancels out. But you really only have to do that, when something cancels out. If nothing cancels out, there's no point to factoring first. Okay, so again, that's an experience thing. I'll let you kind of decide when you think you need to or don't need to do it. Okay, but again, if you don't do it and it turns out that something cancels out, you're going to have one too many dotted lines, and it's going to mess up the rest of your graph. Okay. All right, so now we can move on to the rest of the steps. That means finding the end behavior and then doing your table of points. I'm going to need a little more space here, so I'm going to erase the group factoring work. Okay, and then I'm going to now go to step 1 and then eventually step 3 as well. Okay, so for my end behavior, you already know that's going to be the horizontal stuff, and that's going to be the vertical stuff. Okay, so at this point, if you want to, I guess you could still really do this, but nobody really does. The whole point of breaking this down and factoring and canceling is that once you've canceled out, you should realize that this graph over here, when you're done sketching it, will actually resemble this one more than it did when you looked at it over here. Okay, so the leftover graph that you have here is x over x minus 3 and x plus 2. So when I look at the verticals here, that'll probably be the easiest ones to figure out. X minus 3 and x plus 2 is equal to 0 at x equals 3 and x equals negative 2. Okay, And then with the horizontals, again, it's a case where you have to look at your powers on the top and the bottom. Okay, so real quickly, let's just look at that. So on the top, when you look at it, that's just this x up here. That's going to have a power of 1. And then on the bottom, you might think that you also have 1 because you see an x here and an x here. But remember, you can't evaluate the power till you actually multiply everything out and have it in standard form. Okay, so in standard form, the power on the bottom would actually be x squared, which means we have a situation where a is less than b. And anytime a is less than b, you should already know you're going to have a dotted line at y equals 0. Okay. So if you take all this information now and sketch the dotted lines, that means at -2, we've got a dotted line. At 3, we've got another vertical dotted line. And at 0, we've got dotted lines. Okay? So now all your job left to do is, oh, that was terrible grammar there. All you have left to do then is to figure out what's happening on the left, what's happening in the middle, and what's happening on the right. Okay, so let's create some tables for that. So here's the left, here's the middle, here's the right. Middle and right. Okay, x and y, and x and y as well. All right, so to the left of -2, let's use -3 and -4. In between -2 and 3, let's use, again, I'll just be safe here, so let's go -1, 0, 1, and 2. And then to the right of 3, let's go 4 and 5. All right? And one more thing before we actually evaluate our values, remember that at -3, I'm going to have a hole, right? So what I would do here, just to remind you, is probably just put a little box around here and a little circle next to it to let you know that when you graph that point, make sure that you make it an open circle, okay? All right, so I'm going to take these points now, these 2 over here, these 4 over here, and these 2, and I'm going to plug them back into my simplified equation. So that's x over x minus 3 and x plus 2, okay? And I'm going to see what I get. All right, so when I plug it back in, I get -0.5 at -3. At -4, I get, looks like -0.29. At -1, I'm going to get positive 0.25. At 0, I will get 0. At 1, I'm going to get -0.17. And at 2, I'm going to get, looks like, -0.5. At 4, I will get, looks like 0.67. And then at 5, I am going to get 0.36. Okay? So let me graph those points on our plot over here. So at -3, I'm at -0.5. So really close to the axis, just right below. Key thing here is make sure you put an open circle on it when you graph it, because that's where your hole is located. At -4, I am at -0.29. So just make that just a little bit higher than the previous point. At -1, I'm at 0.25, so that's somewhere above. At 0, I'm at 0. At 1, I'm at -0.17, so somewhere below. And then at 2, I'm at -0.5, so just a little bit lower. At 4, I'm at 0.67, that's a little bit up here. At 5, I'm at 0.36, just a little bit below. All right, so if I now connect the dots and try to graph it, obviously these two will connect over here. And then since my end behavior is here and here, it only makes sense to follow it and sketch my graph like this. In the middle, I can connect the middle like that, and it only seems reasonable to think that we will finish off by going up and following the end behavior here. And then on the right-hand side, I will follow the dotted line going down. And then on the right-hand side, obviously, these two dots will connect, and then I'll follow the end behavior up, and then I'll follow the end behavior across. And that should be my graph for this rational expression over here. Okay. All right, so key thing here then obviously is make sure that you draw the hole over here. Otherwise, you know, this does get messed up. If we look at the features of the graph, you've got that little snake like graph in the middle, and you've got these guys on the sides. Again, they're diagonal away from each other. Makes you think that they have origin symmetry. Long story short, when you look at this graph, it looks like it's got a lot of odd behavior to it. So when I look at the top part of my simplified fraction, that's x, that's an odd function, so it matches up, it makes sense, okay? If this were x squared, which it originally was before I canceled out stuff, but if it were x squared, I would guess that these two guys should more be right across from each other, and then in the middle, I would expect to see a parabola more than I would this little snake figure here, okay? So when I look at the behavior of the graph and I compare it to the top part of the simplified fraction, it does make sense to me, all right? Yeah, so that's your function over here. Again, the key here was you had to know before you started any of these steps to make sure to factor this so that you could see that something canceled out, and when it did, it created a hole, and more importantly, it also eliminated one of your dotted lines. If you had drawn that extra dotted line here at x equals -3, I guarantee you it would have messed up how you thought the rest of the graph should be connected to each other. Okay. Okay, for our last complex example, we've got x squared plus 1 over x minus 4. Okay, so let's get to the steps so you can see what this is going to start looking like. So step 1, step 3, and then step 2, optional, up to you. Okay, so for step 1, again, we want to figure out the end behavior. That's figure out the horizontals and figure out your vertical ones. Okay, so the vertical is the easy one here. That's just set x minus 4 equal to 0. That'll get you x equals 4. Okay. Your horizontal, since this entire thing is in fractional form again with a function up top and a function on the bottom, you want to do your case scenarios. Okay, so up top, your a value is going to be 2 from the x squared, and on the bottom it's going to be 1 from the x. So you finally have a case when you look at it now where a is greater than b, and when a is greater than b, you're not going to have a ha anymore. Your ha is now going to become a saw, a slant asymptote. Okay, so the key here is to note if you're going to be drawing a diagonal line, I don't care what type of diagonal line you're going to draw, you can't represent this as like y equals 4 or y equals 3. That doesn't make sense, okay? The only way to represent a diagonal line is of the form y equals mx plus b, okay? So that means for your slant asymptote, if you're going to write something to represent it, it's got to be y equals something x plus something, all right? Okay, so how do you figure out your mx plus b in here? So it turns out, in order to do that, you're actually going to have to take this and do the division. Okay, so you've got your options. You can do the long division, which I know you love so much. So that's x minus 4 going into x squared. Don't forget your placeholder plus 1. When you do the math here, this will be x over here. Going backwards here, that'll be negative x squared plus 4x. And then that'll give me 4x, drop the 1. X minus 4 goes into 4x plus 1 4 times. Do the math again, going backwards, that'll give me 16, which will give me 17. So last time, if you got a remainder, this sucked because that meant you couldn't trust this. You must have done something wrong. Turns out for this one, because we're not looking for factors, you're actually okay to get this and have a remainder. Okay, that's not going to make this answer any less significant. Okay, in fact, all I needed was this part. I'm not going to add this part in here when I graph it. So technically, when you were doing the work for this particular problem, if you had wanted to just kind of stop right here and not do the rest because you already figured out this part, you are perfectly fine to do that because that's all you need to help you figure out the equation of your diagonal dotted line. Okay. Option 2 for this, because if you look at it, since you are taking a function and dividing it by just x minus 4, so a singular factor, you could have also done the synthetic with this, so just put the 4 on the side. Here we'll go 1, 0, 1. Again, make sure you put the placeholder in here or else everything gets messed up. And you do the math, you'll get a 1, 4, 4, 16, 17. And once again, the 1 and the 4 become x plus 4, and you can ignore the 17. So you would have gotten the same answer as well. Okay. All right, so let's look at what we got so far. So the key here is I've got a diagonal at y equals x plus 4, and I've got a vertical at x equals 4. So when I graph that, 1, 2, 3, 4, that's this one right here, and then hopefully you still remember how to graph a line. So we go 1, 2, 3, 4 here, and then we go up 1 over 1 to graph a line, right? So this will be your diagonal over here. Okay, and then all you got to do now is figure out where your graph is. Now I have a suspicion, because if you look at the regions that I just created here, you've got, it could be here, could be here, could be here, and it could be somewhere up here, which I don't have much space, which I think it actually might be. So what I'm going to do is I'm going to move my little toolbox down here instead. That'll give us just a little bit more space to work with, but obviously I'm probably going to have to fudge this part a little bit because I don't have much room to work with here. Okay. All right, so just like last time, I know this is going to confuse you now because you've got a diagonal line in here, but if you remember the rules, when you are setting up your table, okay, your table always goes by where your vertical dotted line is, okay? Don't all of a sudden try to use your diagonal one to help you figure out what to plug in for the tables, okay? So if you use your vertical, it's at 4 right now. To the left of 4 is going to be 3 and 2. And then to the right of 4 is going to be 5 and 6. Okay, so once again, I'm going to take these values and I'm going to plug them back in here and see what I get. Okay, so when I plug in 3, I'm going to get negative 10. And when I plug in 2, I'm going to get negative 2.5. When I plug in 5, I'm going to get 26. And when I plug in 6, I'm going to get 18.5. Okay. So when we plot these points on here at, what is it, at 3, I'm going to be at negative 10. So 3, I'm going to be, wow, was it all the way down here? And then at 2, I'm going to be at negative 2.5. So again, maybe somewhere over here. And then at 5, I'm going to be at 26. So that, as you can tell, is going to be way the heck up here. I really can't even graph it, so I'll just put it up here somewhere. And then at 6, I'm just going to be a little bit lower. So let's say I'm like somewhere right here. Okay, so if I connect the dots right now, these two obviously connect together. Those two are going to connect together. If you want to continue sketching the graph so that it makes sense, you can already tell that these dots are located in this region right here, right? So after we're done connecting the dots, you probably want to use the end behavior to finish it off. So if I do that, that'll look something like this. Okay. And then same idea up here. Obviously, you're not going to be able to see much. I apologize for that, but I'm running out of room here. But you can already kind of imagine to graph this one over here. Once we're done connecting the dots, we're going to follow the end behavior using these guys. So that will make it go this way, and then this will kind of go up there. Okay, and that will be your graph for x squared plus 1 over x minus 4. Okay, so the key here was, notice whenever you have the slant, it'll form an x when you do the dotted line, And then now you suspect that your graph will either be like this from each other, or sometimes they'll be across from each other like this as well. But the rest of the steps pretty much the same. Okay, so again, with all these graphs, the key is figure out your dotted lines correctly, because without your dotted lines, pretty much everything gets screwed up. Um, with your dotted lines, if you have them correct, it helps you choose these values. Like you saw in the other graphs, if you need to pick more values, don't be lazy. Pick those values so that you can figure out exactly where and how you should draw your curves. Okay?